Greetings, everyone. This is the August 15th, 2023 occurrence of the P4.org Open Source Developer Days meeting. Today we have a guest speaker, Devon Loehr. He's an intern working at Google. Devon, please introduce yourself a little better than that and let us know a little about yourself, and then go ahead.
Sure, thanks. So my name is Devon Loehr. I'm an intern at Google over the summer, as Andy mentioned. When I'm not an intern at Google, I am a PhD student at Princeton, where I'm working with Dave Walker on programming languages and networks. So my main project is this language called Lucid, which compiles down to and is meant to make programming things a little bit easier at a higher level. But that's not what I'm here to talk about. I'm here to talk today about the work that I've been doing at Google over the summer, which is developing a model of the way that programmable network hardware tends to work. And in particular, I've been focused on developing a model for programmable packet parsers. And there's actually another intern here who's developing an analogous model for programmable pipelines. So the reason we're doing this, of course, is to solve a problem, namely that in the modern ecosystem, we've got all sorts of pieces of programmable networking hardware coming out of all sorts of different vendors. And on the one hand, this diversity of sources is a good thing. It means you have room for lots of different designs and nobody has a monopoly on this kind of hardware. But it also has a pretty serious downside, which is that each vendor, when they start and join this space, is going to have to design their hardware completely independently from scratch. And that, of course, imposes a huge design burden on anyone who wants to enter the networking hardware space. You're not just going to have to design the details of your particular hardware, but you're going to have to figure out stuff like, how do I design a programmable packet parser in the first place? Furthermore, because once they come up with their designs, everybody makes their design proprietary, you end up with a situation where each piece of hardware requires its own little ecosystem in order to function. So in particular, if you want to actually write programs for your programmable hardware, you're going to need some kind of compiler. And now, therefore, in order to use your hardware, you're going to need not just a design team to make it in the first place, but a whole compiler developer team in order to actually write the programs for it. Finally, because everyone's come up with their own designs and each piece of hardware is different and idiosyncratic, it's very difficult to predict ahead of time if a given piece of hardware will support a particular P4 program. Often what tends to happen is programs will be developed for a particular piece of hardware and they'll work fine there, but they won't really work anywhere else. And that means that in practice, languages like P4 are a lot less portable than they really should be. The kicker here is that even though everyone is designing their hardware independently, in practice, they're all drawing from the same sets of sources in the literature, meaning that we end up in a situation where lots of real hardware actually ends up looking very, very similar. They agree on a lot of the high-level architectural decisions and differ mostly in low-level implementation details. But because all of these designs are proprietary, there's no opportunity for generalization or sharing across those designs. Instead, you end up with the situation we just discussed, where each piece of hardware has to have its own little dedicated ecosystem in order to work. So the goal of our project is to create that opportunity for generalization by introducing a hardware model of how we believe this hardware can and does operate. And in particular, we want our model to be configurable so that it can represent lots of different pieces of real hardware. And our goal is to release this, our model and the entire toolchain open source so that it can be used and discussed and reused by anyone who wants to. The model that we've come up with, we call CAIRN, a Constraint-Aware IR for networking. And again, I'm going to be talking about specifically the parser model because that's what I've worked on. And our parser model is based on Glen Gibb's prior work on TCAM-based packet parsing in 2003. So CAIRN is designed to basically be a particular hardware architecture, and it's designed to be configurable in the sense that it can be configured to represent different implementation decisions. For example, Our model specifies that packet parsers are structured as a series of TCAM tables, which are executed one after the other. But it does not specify anything about how big those tables are, how many rules they can have, or how long the sequence should be. Those are exactly the sorts of things that vary between implementation decisions. So the first contribution here is the model itself, but we've also created a way of programming the model and a tool chain, allowing it to be used in real life. So in particular, we created a compiler. Really, we've designed it and we're currently in the process of implementing it for translating P4 programs into CAIRN programs. And to get an overview of what the CAIRN toolchain looks like in practice, imagine you're a user wanting to compile your newly written P4 program to some particular piece of hardware. You could do this by invoking the CAIRN compiler on your source file and passing it a configuration file, which the hardware's manufacturer would supply, describing the implementation details of that hardware in terms of our model. So to go back to the previous example, this file would say how many tables are in that sequence and how big each table is on the actual hardware. Our compiler will then produce a CAIRN program, basically a series of TCAM tables, that conforms to the restrictions of the hardware. So if your hardware says you can't have more than 16 rules per table, our program will ensure that no table has more than 16 rules. Once you've got this program, you can use it in a couple of ways. You could either send it to the CAIRN interpreter and basically simulate its behavior. This can be useful for validation or debugging purposes. Or you could pass it to a vendor-supplied backend compiler to produce an actual binary for your particular piece of hardware. And the benefit here to the vendor is that the CAIRN compiler, because our model is fairly low level, has to do much of the really hard work that goes into this sort of compilation process, translating P4 into low-level hardware constructs. And therefore, the vendor's part of the compilation process, translating CAIRN to a binary, ideally should be little more than an assembler. They just have to translate the CAIRN model constructs into whatever the analogous hardware constructs for their particular switch or NIC are. Right? So the benefits of this model are, I think, great. First, the model itself provides a common reference point that people can use when discussing the design of these sorts of parsers, much in the way that Glen Gibb's model has been used so far. And so people can talk about the CAIRN model in general without having to reveal proprietary details about their own designs. Furthermore, it provides a very useful starting point for anyone wanting to design a new piece of hardware. And it provides an incentive to use the CAIRN model, because if you've designed your hardware according to this model, you can reuse the CAIRN toolchain, which is our second major contribution. As I was talking about before, since our compiler automatically handles a lot of the really difficult compilation challenges, it can be used to massively reduce the work of writing a new compiler by essentially starting by using our compiler to produce a CAIRN program, and then writing just the backend, which again should hopefully be very, very simple. And since we're planning to open source the compiler along with everything else, there should be plenty of room for it to be reused and improved by the community over time. The final benefit here is that the combination of our interpreter and compiler makes validating programs much easier. Right now, if you want to know if your P4 program will work on a piece of hardware, pretty much the only way to get any degree of confidence is going to be to actually run the compiler for that hardware on your program and see if it works. But of course, that could take a while, and it requires you to actually have the compiler for that piece of hardware. With CAIRN, all you need is the configuration file, and you can run the CAIRN compiler instead. And if it successfully produces an output, you will have a very strong indication that the program will in fact work on the hardware you've described. So you don't need to have a full compiler for the piece of hardware. And in fact, you can write a configuration file for non-existent pieces of hardware. You could do this in an exploratory manner to maybe design a piece of hardware by testing it out to see what configurations can support certain P4 applications that you care about. All right, so that is the big idea here. That's CAIRN. And what I want to do for the rest of the talk is introduce you to this model I've been talking so much about. I want to give you a high-level overview of how the model works, and then talk a little bit in detail about some of its components. Next, then I want to show you how one actually uses this model to represent a real-life P4 parser. So I'm going to be basically showing you briefly how you can compile a given parse graph into a CAIRN program. And I expect those two things will be the bulk of the talk. Once we're done with that, I do want to talk just a little bit about our compilation process, giving you a quick overview of the compilation passes we're doing and highlighting some interesting challenges that we've run into. Finally, our model is designed to be extensible. So it's fairly easy to add, for example, more constraints to the config file. So I want to talk about some future extensions that we've basically been putting off for now because we've been trying to keep things nice and minimal to start with. So without any further ado, I'd like to jump into the CAIRN model. I believe Andy said this at the beginning, but stopping me for questions is fine. Just note that I cannot see the Zoom screen, so you're going to have to use your voice.
Hello, Ryan Goodfellow here. I just have a quick question. So does this IR fit in the same logical place in the stack that like LLVM IR does in terms of it's above the actual instruction set architecture for whatever you're compiling to, but below the high level language that you're using?
Yeah, I think that's an accurate characterization.
Okay.
Yeah, I wouldn't necessarily. I wouldn't go claiming that this is, as useful as LLVM is for all of its applications, but I think it does occupy that same niche.
Okay, thanks.
Great. So let's talk about this model. And before I discuss our model, I just want to briefly touch on the prior work, this Design Principles for Packet Parsers paper. That was really the basis and the inspiration for our current work. So this, the parser model discussed in that paper is basically structured with three components, and it operates in basically a loop. At each iteration of the loop, it examines some header fields to figure out what the next header is, and also maybe how long that header is or how long the current header is. Then it extracts the relevant header fields that your ultimate packet processing cares about and sends them to a packet buffer where they are stored and eventually forwarded along to your packet processing pipeline. And this is just iterated on. So you're going to match on one header to figure out what the next header is, extract its fields, move forward, match on that header, etc. You could implement this design either in a fixed function way, where you're always looking for the same headers and field values and taking the same actions, but you could also make it programmable by using a TCAM table to store and potentially change on different runs the particular header values you're looking for and what actions you're taking as a result. Right? So that's sort of the basis that we're drawing from. But there are several differences between our model and this one. A big one is that in this model, you've essentially got one big TCAM table that is iteratively matched against multiple times. Our model, instead, is structured around a series of TCAM tables, which are matched against one each in order. So this is a high-level overview of what our architecture looks like. And it's important to note that our logical model is describing a parser that parses a single packet at a time. So we've got this global stack of memory that can be read and modified during parsing. And again, there's only one packet in existence at any given time. So we don't need to worry about like splitting up that memory between packets or anything. So the bits of the architecture that we're showing here are, again, a glob of memory that can be read and written, our series of TCAM tables, and the packet that we're reading from, which also has a cursor indicating where in the packet you can read that moves monotonically forward over time. The sequence of how this thing actually works is we're going to start at the beginning, and each table will match its key patterns against certain values drawn from memory. And this is a standard TCAM match. It will select some action, the first one whose pattern matches, and those actions will modify the state of other things. So they can do things like move the packet cursor forward, read from the packet, or modify memory by copying values around. Once the actions of this stage have executed, we'll move on to the next stage, which again matches its patterns against certain keys and takes some actions. And it's worth noting that these actions all happen simultaneously within a given stage. So any side effects of one action, like moving the cursor forward, won't affect any other actions in that same stage. They're not visible until the next stage. And so, of course, we just keep doing this until we get to the end of the series of TCAMs, at which point parsing completes and, hopefully you're in an accept or reject state. One very important thing that our model assumes is you might have noticed that each of the TCAMs is drawing its keys from the same locations in memory, and that's not an accident. Our model specifies that each TCAM matches each column against the same chunks of memory. And therefore, it's very important that the CAIRN program or the compiler, translating a P4 program, will put whatever values it wants to match against into those locations in memory before it does the match. So the actions here in stage 1 are going to be responsible for setting up the match in stage 2 by copying whatever we want key 1 to be into this blue location and copying key 2 into this other green location. Okay, so that's the high-level view of our architecture. You've got this series of TCAMs that match against memory and a packet with a cursor. The other parts that we've sort of glossed over that now I want to touch in more detail are, first, the way that we actually do the job of being a parser, which is extracting headers. So the way we model the headers that our parser has extracted, and so how it's structuring the packet, is quite simple. We've just got a string indexed map where we store the extracted headers indexed by the name the program gave them, and the thing we store is where that header begins in the packet. We're assuming here that we know from the program what the structure and size of these headers are, so we're not bothering to store where they end, but of course you could do that as well if you wanted to. Here we're saying that we've stored the Ethernet header starting at offset 0 in the packet. And if we execute this extract header action, it's saying we should extract the IPv4 header from the first 160 bits of the packet. Packet locations inside of an action like this are always relative to the cursor's current location. So this first 160 bits of the packet really means the first 160 bits starting at location 12 or maybe 14 because we're in the middle here. And so when we extract this IPv4, you can see that we've recorded it starting at that offset there, the absolute offset, rather than the value actually written in the program. And then, of course, we move the cursor forward using this move command after extracting the header. The final major piece of the model that I want to talk about is that memory from our prior image. Before, I presented it as basically one contiguous blob, but really, we're modeling memory as a collection of what we call data stores. So data stores are basically a generalization of registers. They're fixed-sized chunks of memory that can be read and written during parsing. The specification of which data stores exist is part of the hardware's configuration. So here, looks like we've got 3 data stores named R1, R2, and metadata. R1 is 16 bits wide, R2 and metadata are 20 or maybe more bits wide. The thing you can do with data stores is, well, read and write them. So for example, if you take a copy data action, this is saying we should copy the value from the bits 8 to 15 of the packet into the first 8 bits of R1. Remember that packet locations are relative to the cursor, so 8 to 15 is really these 2 nibbles here. And so if we execute this action, we'll just copy them into R1. We can also just as well read between data stores, so we could copy, for example, the first 15 bits of metadata into the first 15 bits of R2. And that's just a very direct copy left to right, starting at the beginning, ending at the end. So data stores can be used in practice for a number of different purposes. They can be used to store information that maybe you want to match on later in your parser. You could use them to store, say, parser arguments that you want to reference at some point. But very importantly, you also use them to store the keys of the TCAM. So like I mentioned before, certain locations in memory will be designated by the hardware configuration file as the key locations. In this case, we've designated the first 8 bits of the R1 store as the first key, meaning that the first column of every TCAM will match against whatever value happens to be in these 8 bits at that time. And you can see over here that the pattern we've put here is 8 bits wide, just like the key location. Similarly, we've also designated the first 16 bits of the metadata store as our second key, meaning that the second column of every TCAM will match against whatever value happens to be in these 16 bits. And again, the pattern is an appropriate length. All right. So that's really the main features of the model. The last thing I just want to briefly talk about are the actions that you're allowed to do inside of TCAM rules. And we've got a very minimal set of basic actions that we've actually seen all of them before. The 3 actions you can do are moving the cursor forward by n bits, extracting a header with a particular name from a particular location within the packet, and copying a value into a location. And as mentioned before, all of the actions in a given rule are executed at the same time. So if they have side effects, those side effects are not visible until the next stage. And that's the model. So to summarize, the important pieces here are a series of TCAM tables in order, the map storing the headers that we've extracted that will be presumably used by the packet by the program in the packet processing pipeline, the packet that we're parsing, a cursor moving monotonically forward, and a bunch of data stores, each of which has a name, a width, and some locations which are designated as storing the keys. The very last thing I want to talk about here is just to show you what one of these configuration files looks like. So we've come up with a little configuration language, which is really just a dialect of JSON. So this is a simple configuration file specifying a particular piece of hardware. In this case, it specifies 4 data stores, each of which has a name and a width and some other properties, like whether it's readable and whether it's writable. And we also specify what the keys are. In this case, we've designated the first 32 bits of the state data store as storing the first key, and all 32 bits of the R1 store as storing the second key. Finally, it contains any constraints about the hardware. For example, the total number of stages available, so we get 32 TCAM tables, and the total number of rules that are allowed in each table, in this case, 16. All right, so that is the model. So the next thing I want to do is go forward and show you, again, how you use this model, how you can translate a parse graph into the CAIRN structures. But I think this is a good time to stop and take questions.
Yep. I don't want to inundate you with examples, and I imagine Glen Gibb, who's actually here, could give many more, but you'd be surprised at how much variety there is in hardware parsers out in the world, I imagine. And it's like you tell a hardware designer to optimize something to the nth degree because they need to do it at 100 terabits and fit into this much area and power, and like all kinds of constraints pop up that you might not imagine before you start that process. So for example, like how many bits can you copy to and from these stores and the packet on a single stage? 2, 16, 8, I know, I think I've heard of parsers that have all of those constraints in different designs. Some of them don't even extract headers. They just remember offsets in the packet. Anyway, I'm not claiming that you should try to cover all those possibilities. In fact, one of the goals of your work could be, we should standardize on something that fits within this mold and these variations, and not continue to create variations on those unless there's a really strong factor to gain in some critical cost constraint. Anyway, just thought I'd mention that, and not intended as a criticism, other than just like, to somebody who's slogged through this for years, it's like sometimes there are actually reasons to go off book on some of these things.
Yeah, I mean, so that's a really good point. I think my 2 responses would be, first, the things like how many bits can you read and write at once, for example. That's exactly the sort of thing that could be represented as a constraint in our configuration language. So that's actually, that's I think, a strong argument for this model. The things we have to worry about are things that are significantly different, that like don't use a series of TCAMs at all. or do their own completely unique thing. And that brings me to the second point, which is I think, as you've noted, this model is, to use one of my colleagues' favorite words, opinionated. We are, sort of saying we think that your parser should be like this. And one of those things is, again, using a series of TCAMs. There are also some other things that are sort of baked in here, like each stage of the parser executes in a single logical clock cycle. There isn't any worrying about like syncing things up. So it does mean that we are excluding things which deviate wildly from it. But we're also, I think, we are trying, we are at least trying to sort of enforce this standard and say, we think you should do things like this. And hey, also, if you do things like this, you can use our tool chain, and that will be much easier for you than doing everything from scratch.
Perfectly reasonable answer. Anybody else have any questions?
I have a question. Thanks, by the way. And you may not be able to answer this, what's the motivation for this work? Besides, motherhood and apple pie reasons, which you gave up front, which are good ones. In other words, we want a standard model, there's all these benefits, but what's the real motive? Is there a motivation, like industrial motivation for this, let's say, or commercial, that you can disclose or not? Just
yeah, I mean, so this project, frankly, has gone through like at least 5 different justifications in the 10 weeks I've been here. So some of them are, the ones I said before, like it's very nice to have it. I do think a big part of the industrial motivation is that, again, like having the model makes it much, much easier to manufacture this hardware for someone who wants to follow along. So you can't, like, again, using our compiler is much, 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 much easier than writing your own compiler from scratch. At least ideally, because our compiler handles a lot of the really complicated compilation work that otherwise everybody is implementing and re-implementing secretly because they're not sharing. And so they need to write everything from scratch themselves.
Is the hope that vendor, because there's kind of three, I think of 3 categories of, parsers that P4 would care about. Switching ASICs, which, there's not too much development going on in switching ASICs in P4 that's commercially accessible to everyone yet. But, we know there's certain vendor out there with 1 or 2. FPGAs, which, you can really get in there and mess around with the VHDL code and or the tool chains, or the Verilog, I should say, whatever. And then SmartNICs. So who of these categories would take up a tool like this, and how would that play out in the industry in the ideal world? I mean, how's this really going to realize itself in real actionable stuff that we all could see the results of? Does anyone have a guess for that, or a hope?
I do. I have a guess.
Yeah,
whether it'll happen.
I'm just so curious about the practical applications of this. I like it, but I'm wondering where out of the lab.
I don't have a guess on how realistic this is to happen, but this could nudge hardware designers into a more common mold than their current diverse capabilities. Long term, not like this generation of ASICs, because that's done. Maybe not the next generation of ASICs, because they're already partway done. And backwards compatibility rules often across 2 generations of ASICs. But 2 generations later, 3 generations later, maybe.
Yeah.
Or some dark horse that we don't know about yet that wants to undercut us all and says, hey, great, we got some tools for free.
Yeah. Interesting. Because
yes, I mean, it's hard to be a dark horse and get $100 million in funding to do an ASIC design and all the software for it. So but this makes the software cheaper. Not the ASIC cheaper, but the software.
Yeah, so if this work is impactful enough, it might have an impact, I don't know, same scale of impact, but similar in terms of its long-term effect is RMT architecture, right? These papers that said, here's what RMT is, and look at the effect it had, decade later, right?
I mean,
maybe this will plant some seeds that turn into a more universal way of doing certain things.
But I mean, open source CPU designs exist now. Like you can get download Verilog. Has that dominated the industry yet? No. Will it soon? Seems hard to believe, but it does put a downward price pressure on the proprietary ones, right?
Yeah, it gives people choices, right? RISC-V, C of course, things like that.
Yeah,
Cool.
but I mean, what has dominated the industry in the CPU space is CPUs with open instruction set architectures, because that has allowed ecosystems to spring up around those CPUs. I think what we're talking about here is a bit different. It's at a higher level, like the intermediate representation of a compiler. But I mean, maybe this can drive toward open ISAs, which, you know, I personally think is something that will be necessary for programmable networking to survive at all.
Oh, that's a cool idea.
Yeah, I think that makes sense. All right, any other questions about the model itself?
So I have one quick question about constraint. So the hardware target that I'm very used to compiling for, everything out of the parser goes into a packet header vector, which has like a very regular structure. It's a set of fixed size cells, and you just have to live with the size of those cells and how you're going to pack data into that. Have you considered that in your design for the IR that you've come up with?
Yeah, so if you recall, I mentioned briefly right at the beginning, there's another intern working on an analogous model for packet processing pipelines. And so PHV constraints are something we're considering as part of that model, but not this one.
Okay, but the output of this model will ultimately have to feed data into a PHV like memory
It'll get
architecture.
piped in, but we haven't really thought too much about the interface between them until the other model is more mature.
Okay, thanks.
All right, any other questions? Okay, then let's keep going. So now that we've seen the model itself and all the components, I want to show you how we can represent a particular P4 parser in terms of this model. In other words, I'm going to be showing you a little bit of a compilation process, turning a P4 parse graph into a CAIRN program that is a series of TCAM tables. So we're going to be starting with, as I mentioned, a parse graph representation of a P4 parser. If you're familiar with P4 parsers, it's hopefully obvious how you can directly turn one into this sort of parse graph. And the structure of the parse graphs that we're using has the following important components. First, it's worth noting that we only consider DAGs. So if your parse graph has loops, you're going to have to do something about those before giving it to CAIRN. And our parse graphs are state machines with the following components. First, each state has an ID number, which can be referenced numerically by TCAM patterns. Each state has several actions, which just come from the actions in the P4 program. Here, they're just extracting headers. And finally, the transitions between states, which would be select statements in P4, are sort of split up here. When you have a select statement, the keys that you're matching on are designated by this special set key action in each of the states that wants to match on something. So here we're matching on ether type, here on IPv4 source address. And the patterns that you match against are represented as annotations on the edges of the graphs. So here we're saying this edge should be taken if the ether type field is OXO800. And we'll go over here instead if it's 860D. Because these are TCAM patterns, they might have wildcards and overlap. So we've also assigned each edge a priority saying just how to disambiguate if a value matches multiple patterns. All right, so again, hopefully it's pretty easy to see how this pretty directly represents a P4 parser. And the question now is, given one of these parse graphs, how can we represent it as a series of CAIRN TCAMs? And the key thing we're going to do here is, perhaps unsurprisingly, we're going to use the TCAM's match action abilities to represent the transition between states. And so in particular, we are going to copy these key values into the designated key locations of the configuration file so we can match against them. So the first thing we're going to do when we're compiling this is examine our configuration file, figure out what space we have available to store keys. And then we're going to start translating these edges one by one into rules. So the way we translate a particular edge is essentially it has three parts. First, the edge will match on, the rule will match on the source node of the edge. So we're saying if we were previously at state 1, we're matching this edge. Then we will match on the edge's annotation. And notice that we have chosen to store the key value for this edge in our second key slot, R1. And since the R1 slot is 32 bits wide, but our pattern is only Oh dear.
Problem I can help with?
Yeah, 1 second. Someone might be trying to take the room, which would be unfortunate.
I wish I had a commercial announcement to throw in right now. Intel IPUs, awesome. There's a really short commercial.
I particularly liked Ryan's comment about the need for standardization.
Sure.
Thanks.
No,
Appreciate it. It's yeah, it's we sit in kind of a different space as a lot of the vendors. We're a system integrator, and so that's something we really believe in. But I believe the speaker's back, so I'll send it back.
Yes. All right. Sorry about that. Fortunately, the next stream over was available. Not quite sure how I lost the first one, but anyway, the point is when you're translating an edge into a rule, you will first match on the source state of the edge, then you'll match on the edge's pattern. And in order to do this match, you have to decide where in memory you're going to store that key, and you need to write your pattern to match. So here we've chosen to store the key into the first 16 bits of the R1 data store. And so our pattern matches. We're matching against the first 16 bits here, and then we've padded the rest of it with wilds to make the pattern the same length as the location. Finally, the actions of the edge are the actions of the destination state. So hopefully it's not too hard to see that these actions here are basically a CAIRNization of the actions of the IPv4 state. In particular, we are extracting the IPv4 header from the first 160 bits of the packet. And we are also translating the set key action here as a pair of copies. In particular, we are copying the source address field directly from the packet into the R1 data store so we can match on it in the next stage. And we're also copying our current state's ID into the state data store. So again, we can match on it in the next stage. So that's basically how you translate a rule. If we kept going, we could then translate this next rule. It's basically the same thing. We match on the ID of the source state, the pattern of the edge, and execute the actions of the destination state. The only difference here is that we are not setting a key at the end. So we've only got one copy, which is just designating what state we are currently at. So you can then go through this basically edge by edge and turn each of them into a rule. One little tricky thing is that at the beginning, the source node has no incoming edge, so its actions will never appear anywhere. And we account for this by just adding a single catch-all rule in a separate TCAM table. So this is its own table before. So this is its own table. That was one line shorter a minute ago. This is its own table before this second table here. And you can see we just unconditionally execute the actions of the start state, which will get everything set up for us. All right, so if we keep going this way, we can translate these bottom three rules. Their actions are much simpler since we're just going to accept or reject. The only thing we do is copy the ID into the state field to mark that we're there, and that's it. All right, so hopefully you believe me. If you don't believe, or hopefully you're convinced, and if you don't convinced, you can take my word for you can take my word for it that this series of 3 TCAMs, 1, 2, 3, when executed in that order, precisely implements the semantics of this P4 parse graph. The very last thing I want to talk about in this section is, again, showing you what the sort of output for this looks like. We've got a JSON-based representation of our IR, and it's a very straightforward representation of these TCAM tables. The JSON is just a list of tables. Each table is a list of rules, and each rule is just a combination of some annotations saying where it exists, just for convenience, as well as the patterns that the rule matches on, and the actions to be executed if the rule is matched. All right, so the output of our compiler is one of these JSON CAIRN programs, And that's the input that this is the input that our interpreter takes and that any backend compiler might take. All right, so that's all I wanted to say about representing things. I think this is another good place to stop and take questions before we move on.
Please go ahead. I've got one if nobody else does. I'll ask mine then. So given the example constraints, I think one of your example constraints was number of TCAM entries per stage.
Yep.
So I could imagine a smart enough compiler saying, "Oh, if everything was easy and simple, I would put this many TCAM entries in this stage, but you don't have that many. You could put a subset of them in one stage and then have a catch-all rule that goes to a special synthesized state in the next stage that uses more TCAM entries to finish the branch." Is your compiler that fancy yet, or?
So our compiler is again still being implemented, but we've designed all the code, but writing it in C++ is hard. Yes is the short answer. It turns out you don't actually need an intermediate synthesized state because the way our rules are structured, after the starting rule, you will always match precisely on the previous state ID, meaning that you never need a catch-all state basically, because you will never you basically just put all the rules you can fit in one stage and then keep going and put all the rest in the next stage. And if you don't match any of the rules in the first stage, you will just naturally follow through into the next one.
And depending on the constraints and the P4 program, there's a lot of reasons why you might spill things over into following stages.
Yeah, and I'm actually going to be talking
not enough
about
ability to copy bits between, not enough ability to extract bits for large headers.
Yeah,
those
so
are
I'm
all
actually
kinds of things that tend
all
to.
of this a little bit later on.
Great, I'll wait.
Yeah. Some parts in more detail. All right, any other questions? All right, then let's talk about our compiler. So as mentioned, this is in progress. We're still implementing it, although we know what it's supposed to do. We've designed all the passes. The goal of the compiler is to take a P4 program and a configuration file for a particular piece of hardware and output a CAIRN program, which corresponds to that configuration. So what I want to do here is first just give you a quick overview of the main passes of the compiler. So first, we go through and convert extract and look ahead calls from P4 into extract header actions and copy data actions in CAIRN. The next several steps are all just replacing references to P4 stuff, usually P4 variables, with references to CAIRN stuff, locations within data stores or the packet. So we translate references to headers that have been extracted to references to the actual corresponding location in the packet. We allocate memory within our data stores to store parser arguments and global variables, and then replace references to those things with references to the appropriate locations in the data stores. And finally, we allocate memory to store each of the keys that we're matching on at each stage. And this is an interesting one because the hardware might have restrictions on how many keys, or like on how much you can match. You've only got so many bits allocated for storing keys. So if you try to match on more than that, you're actually going to have to split up your state and do the match in several phases. And so that's challenging both to make sure you're doing it correctly and then going further, trying to do it optimally. The final step is the one we were just talking a little bit about, which is assigning rules to stages in the TCAM. And again, there are some interesting optimality considerations to think about here in the order that you assign things and how you're able to assign things. So that's the high-level view of the compiler. The bits I want to talk a little bit more about now are these bottom two passes, because I think they have the most interesting challenges that we've faced so far. So the first one, as I mentioned, is here we've got a very simple graph that matches on the first 16 bits of the packet and transitions to some state A, B, or C based on that. If your hardware allows you to match on 16 bits at once, then this is easy. You just translate it very directly the way we were doing. But if your hardware, say, only allows you to match on 8 bits at once, you can't do this directly. You're going to have to split up the match. So one way you might do that is to match first on the first 8 bits of the packet, and then you go to some intermediate state, and then you match on the remaining 8 bits of the packet, and you'll do different things based on which intermediate state you're at. So here the key 0 goes to B, here it goes to C. All right? So this is the sort of transformation you need to do in that case. But actually doing it correctly is a little bit difficult, because when you start splitting up your match statements, you have to consider basically all possibilities for the key values that you're not matching against. And essentially, what this ends up needing is you need to consider not just which individual rule you match, but all combinations of rules that you might match. And essentially what we need here is, instead of a first match TCAM, which returns the first rule that matches in the ordering, a multi-match TCAM, which returns all rules that you could match, regardless of where they are in the order. Fortunately, there's some prior work from 2004 which describes an algorithm for implementing multi-match behavior using first match TCAMs, so we draw on that. And the other worthwhile thing mentioning here is that the order in which we match, basically the order in which we split up our keys, actually makes a big difference in the size of our graph and basically how much intermediate stuff we need. In short, especially in the presence of wildcards, if you say, like here, we matched on the first 8 bits of the packet and then the next 8 bits of the packet, but we could have done it in the other order. We could have matched on the next 8 bits and then the first 8 bits. Or we could have done something weirder. We could have matched on the middle 2 bits and then the outer 2 bits. Right? So we could have split this up in multiple different ways, and the different methods of splitting it up might have resulted in different intermediate states and therefore different amounts of space taken up on the hardware. So actually doing this match splitting optimally is a really challenging problem that we haven't really figured out. We've only just started thinking about it. The second interesting compilation challenge that I want to talk about is what Andy was talking about earlier, is basically allocating our rules or edges, because there's a one-to-one correspondence, to stages in the TCAM. So to see some of the challenges here, consider this parse graph. We've got 6 edges, and when we allocate these edges to stages, the most important constraint is that each edge has to occur after all the edges before it. So this edge 5 must go strictly after edge 4, but it can go anywhere relative to, say, edge 3. So let's imagine we're allocating to a piece of hardware that allows 3 edges per stage. Then one way to do it would be like this. We allocate basically just going left to right. We put the first 3 edges in the first stage, and then edge 4 gets shunted to the next stage because the first one is full. And then because 5 and 6 have to go after 4, they get shunted to this third stage, number 2. And so overall, we've taken 3 stages. But instead, you could have potentially allocated your edges like this, because there isn't necessarily a constraint between edges 3 and 4. You could instead put edge 4 in stage 1, in stage 0, I guess, and edges 3, 5, and 6 in stage 1, taking up a total of 2 stages. The challenge here, though, is that in this case, because edges 3 and 4 have the same source node, they're going to have a different relative priority to each other. And so it's only safe to do this if you know that the patterns on edge 3 and 4 are disjoint, meaning that it doesn't matter which order you match them in. So actually doing this allocation optimally involves reasoning about stuff like the length of paths in the graph. So we'd like to put 4 earlier because it's part of a longer path, but also the relative priority of edges and how the patterns of those edges intersect. So to sum up this part, I just want to briefly talk about optimality as a whole. I've been mentioning it a lot so far. Our compiler right now is not an optimizing compiler. Our goal is just to, produce some CAIRN program that hopefully meets the stage constraint, but definitely meets all other constraints. So in other words, we're trying to compile to as few stages as possible. And that there is plenty of room for optimization in our algorithms. So we've already talked about how match splitting and assigning edges work. But there are some other interesting things you can consider doing. For example, if you have nodes, for example, with an unconditional transfer between them, you might be able to merge those 2 nodes together and do all their actions in a single node, assuming you obey all the other constraints. Another sort of sneaky thing you can do is if you have 2 edges going to the same state with similar patterns, for example, For example, as a result of match splitting, you might have two edges with the same pattern going to the same state, but coming from different sources. You might be able to combine those edges by cleverly assigning node IDs so that you can combine the two source IDs into a single pattern. So that would reduce the total number of rules that you actually have to represent your graph with. All right, so the final thing I want to talk about is just some future work that we have yet to do, stuff we want to add to the model or have considered adding to the model, but haven't so far, mostly because of time constraints and because we want our initial version to be nice and minimal. So the first thing that we want to add is a way of explicitly modeling arithmetic computation during parsing. Right now, the way we model this sort of thing is just by allowing arbitrary arithmetic expressions as part of our actions. So you can write stuff like this. We've got a little nested expression language using the plus, minus, left shift, and right shift operators. And this is great theoretically. It's very easy to write, very easy to interpret, very hard to implement in hardware. You're not going to have arbitrary amounts of computation at each stage. So in the future, I think what we want to do is we are going to want to explicitly represent ALUs that are available on the hardware. And so I imagine a configuration file that defines what the ALUs are, what operations they support. And I expect we can also represent the inputs to each ALU in the same way we've represented the keys for each TCAM. And that means that our compiler will take on the burden of making sure that all the data is in the right places at each stage of the parser. And of course, that means that vendor compilers later on won't have to. The other places that this model is ripe for extension are adding additional constraints to our configuration file. So right now, the only constraints we consider are the number of stages and the number of rules per stage, but there are lots of other realistic constraints that we want to enforce. For example, you can't do arbitrarily many actions at once. There are going to be restrictions on how many of each kind of action you can do per stage, and maybe also on which combinations of actions can be done at the same time. In practice, there's also limitations on how far away from the cursor you're allowed to read. So instead of a cursor, you've really got a window that's moving monotonically forward. So we'd like to represent that explicitly. And then maybe there's some other stuff, like maybe your hardware is set up to only read and write stuff in bite-sized chunks. And of course, right now, our extracted header map can get arbitrarily large, but in practice, you've only got so much space for storing that. The final place that's easy and ripe for extension is adding additional attributes to each data store. So I glossed over this in the past, but each data store has several attributes beyond just its name and width, including whether it's read and writable, and some other stuff, like whether its value persists after parsing, in which case the packet pipeline program later on will be able to read that value and do stuff with it. So we found that representing things as data store attributes can be a really intuitive and useful way of representing hardware constraints. So for example, we might want to include restrictions on which stores can read and write to each other as an attribute of each data store. So each data store is basically annotated with who it's allowed to write to, who it's allowed to read from. We could also represent things like how many times you're allowed to write to each store. So maybe one store allows you to write twice per stage, while the other stores only allow one, for example. And again, we could think about enforcing some kind of alignment restrictions. For example, a data store that is specialized for representing flags might only allow you to read and write single bits at once, whereas maybe generally you only allow 8-bit writes. So that's the future work. To sum up, we've produced the CAIRN model of packet parsers, which is a particular practical architecture for how one might design an actual hardware packet parser. And the benefits of CAIRN are numerous. First, it provides this common reference point that can be used to discuss hardware design for packet parsers. And the model, in combination with the compiler, significantly reduces the difficulty of individual manufacturers and vendors who are trying to design and sell their own hardware. Instead of doing everything from scratch by themselves, if they choose to design their hardware along the lines of the CAIRN model, they not only have a starting point, but they can reuse our tool chain, including our compiler, which will automatically do much of the difficult work that they would otherwise have to implement manually. As mentioned before, we are planning to open source all parts of our model, including this toolchain, so it can be freely accessed and reused and hopefully improved by anyone who's interested. That is my talk. Thanks so much for listening. I guess we're over time, but if people have questions, I'm happy to stick around for a bit.
Are you using any part of P4C front end?
Yes, thank you. I forgot to mention that we are implementing our compiler as an extension to P4C. So that means that not only do we get to use it as a front end, but anyone who's using P4C already can access the compiler easily by just plugging it in as a backend.
What does your IR look like tangibly? So when you compile something with the compiler and you get presumably a file on the other side?
Yeah, it looks like this.
Sorry if I missed it. Okay. Oh, so this was the, okay, so it's the JSON.
Yep, it's just a JSON file,
Okay.
which is a very direct representation, lists of rules.
Okay, and so this is where the ALU discussion came in, and on the other side of that, like if you wanted to represent like arbitrary if then else control flow inside of a parser or something like that, it would need to go to more of like an instruction style representation, I imagine.
Right. If you wanted to represent that kind of control flow, I think you would need something different. I think that's not a very good fit for this sort of very linear pipeline of TCAMs.
The open source P4C today supports if statements in parser states, but it turns them into transition select statements and additional states if needed, I believe.
Yeah. So as long as you're just doing straight line branching, then yeah, you can use that transformation.
Okay, thanks. Appreciate the talk.
Yeah, Devon, this was awesome. Any other short questions?
Hey, Devon, it's Glen Gibb here. Really nice work. I definitely appreciate seeing what you're doing. Just wondering, do you currently have an ETA for when you're going to publish this work? Because I'm assuming you haven't yet published anything on it.
Yep. That's a good question. I suspect we might publish a workshop paper in the relatively near future, but I think otherwise not for a while. Sure. Certainly, we want the compiler to be fully implemented before we publish about it. And that is really just in the beginning stages of actually writing the code because I'm not very good at C++.
Ryan has a solution for you. Ryan's wanting to say it. I'll say it for him. Do it in Rust. Right?
Your favorite language.
Sorry.
Camel, whatever.
Yeah, thank you. Thank you very much. I appreciate it. I didn't even have to say anything.
No, I did it for you.
Camel is my preferred language, but yeah. So
do it in what you want or what somebody will pay to do.
Pretty much. So yeah, the answer is, I think, a real publication. I'm hopeful that one will come out of this, but probably not for a while.
Well, I'll keep my eye out for it in the future then.
Yeah, please definitely do let us know if you have any updates or open sourcing. I think a lot of people here would be interested in being able to see it when it's published.
Yeah, so. So we are planning to open source the parts that we have, which is basically the description of basically the design documents, the description of the model, and the compiler design passes in English and pseudocode, and also importantly our interpreter, which is written in Python and therefore complete. So that stuff, I think we're hoping to publish before the end of my internship, meaning by the end of next week.
Oh, cool.
But we're working on the details for doing that, so we'll see.
Yeah, feel free to send an email. Oh, go ahead.
I think I was going to say the same thing you were going to say, Andy. Is that would you mind sending out a note to the P4 dev group when you do publish something?
Sure.
Yep. Great minds think alike.
Thanks. Nice work.
Yep. Thanks, everybody. And I will stop the recording here and